Hi, welcome to Bloom. In the last lesson, we learned about number systems, which is useful for representing data in computer systems. We learned binary, octal, and hexadecimal number systems. In today's lesson, we will learn how to represent negative numbers. So let's proceed. How to represent negative binary numbers in a computer system. We can represent the minus sign with the help of an extra bit or flag, which is called sign bit or sign flag. We can represent magnitudes with their negative values using three methods: sign magnitude method, 1's complement and 2's complement. Now let's see what are these systems. Sign magnitude. For n bits register, the most significant bit will be the sign bit, and n minus bits will be the magnitude. Let's see an example. How to represent plus 6 in binary. This value 6 will be represented using 110, and the most significant bit will be reserved for the sign. Here it's plus and we use 0 to represent plus, and we have put the value, absolute value here, and the rest of the positions will be filled with 0. And then let's see another example. Let's see how to represent minus 6 in binary sign magnitude method. It's again we know the absolute value 110, and since it is negative we can use 1 for minus value. Then the remaining positions will be filled with 0. So it is very easy. 0 for plus, 1 for negative, and we represent the absolute value and fill the other bits, remaining bits with zeros. So for 8-bit word, only 7 bits are dedicated for the absolute value, and the most significant bit will be reserved for the sign value. So in 8-bit, normally in an 8-bit word, we can represent 2 to the power 8 minus value. But in sign bit, since 1 bit is dedicated for the sign, we can only represent 2 to the power 7 minus 1 maximum value, and the minimum is the negative of that. But in this representation there is a problem. For 0, we can put the binary representation for 0 is all zeros, and here what we can put, is it 0 or 1. So there's an ambiguous representation of number 0. This is the problem of sign magnitude. So that's why there have been other representation methods introduced. 1's complement. Let's see how to represent negative numbers in 1's complement. So first let's take the previous example, plus 6 in 1's complement method. Same as before, the 7 bits are dedicated for absolute value, and the most significant bit is reserved for the sign value. So 6, 110, and since it is plus we use 0, and the remaining positions are filled with 0. So when we are converting this plus 6 to minus 6, it's very simple. We have just to invert zeros to 1 and 1s to zeros, just using a NOT gate to convert it to negative form. So when we convert, 0 becomes 1 and 1 represents negative number, and all these values are inverted, zeros to 1 and 1s to zeros. So this is the representation of minus 6. Again here, as same as previous, there's an issue. Let's say we have 0. The binary representation of 0 is all zeros. So when we invert zeros to 1, all the 8 bits become 1. Then since there's a change in the sign bit, we see plus 0 and negative 0, which again causes two representations for 0. Then there is again an ambiguity in representing 0. To avoid this problem, 2's complement has been introduced. This is the most used representation method in computer systems. Let's see how to represent values in 2's complement. We have plus 6 represented in 1's complement in this way. Most significant bit 0 and the absolute value is represented in the remaining bits 110. The remaining bits are 0. Then we to make it minus 6 in 1's complement, we invert all the bits 0 to 1 and 1's to zeros. So here we get minus 6 in 1's complement. Then what we do is we add 1. We add 1 to make it minus 6 in 2's complement. So we add 1. Then let's see what happens. 1 becomes 0. 1 the 1 is carried forward. Here 0 1 1 1 1. So this is the representation in 2's complement. When we have 0 in 1's complement plus 0, all are zeros. When we invert, all become 1. Then if we add 1, again all become 0. So there's only one method 0 is represented in 2's complement. Only one way, that is all zeros. There's no ambiguity in representing 0 in 2's complement. That's the advantage of 2's complement over 1's complement. So let's see how again demonstrated this. 0 and when we convert it to 1's complement, all becomes 1. In 2's complement we add 1 and again 0. Now we have come to the end of our lesson. Thank you for watching. Please watch part 3, character encoding with blue.